about series. The first question that I want to right now put is an easy question. Just let me know, what do you think this series particular? So let us consider the series that is given by summation an, and where a1 is equal to 1 and an plus 1 is equals to cos of an. What can be said about the convergence and divergence of summation an, where an plus 1 is given by cos of a. So if you remember, and if you can go back and see my video, I'll put that into my description. The video concerning this particular sequence, I have already proven that if this is how your sequence is, that an plus 1 is equal to an, and let us say an lies between 0 and 1. Okay, I have proven that this particular sequence converges to a unique root of the unique root of cos x is equal to x. Okay, even if it is given like equal to 1, because after all an lies between 0 and 1 only. If cos an is like this, so an would lie between 0 and 1. So basically, if an is this way, so otherwise, you know that if it is a1 is this 1, then a2 would be certainly, so like if I want to include here, so if I know that, if I know about this sequence, that is an plus 1 is equal to cos of an, this sequence an goes and converges to x naught, where x naught is a unique root where cos x is equal to x. So what is cos x is equal to x? So let's say I make a graph of cosine x, and this is x. So basically this is that particular point x naught, where cos x and x intersect each other. Indeed, this is a non-zero point. Now just think about this series, summation an, where an is nothing but it is equal to cos of an minus 1. And I know that where does this an converge? This an converges to x naught. And if an converges to x naught, then an minus 1 converges to what? Again x naught. So basically it will be like an converging to cos of x naught. And cos of x naught would be x naught, because after all x naught is that point where cos of x naught is equal to x naught. And certainly this is non-zero. So limit an is such, summation an is such that limit an is non-zero. If limit an is non-zero, it implies that summation an is divergent. So I hope. Okay. Now let us consider an important topic, which is called as the sequence of arithmetic means. Sequence of arithmetic means. Okay. Now it states that let an be positive, then an converges to L. Then an converges to, let's say, first 0, let me take, then Sn given by a1 plus a2 plus a3 dash 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 an upon n. This particular limit also converges to 0. Let us see how. Okay, let us see how. So see, I understand that an converges to 0. That means an minus 0 mod can be made less than epsilon by 2 for all n greater than equal to some natural number, let us say capital N. What does it imply? It implies that an mod can be made less than epsilon by 2. It implies that an plus 1 mod can also be made less than epsilon by 2, and so on and so forth. Okay. Now, what I'll do, also understand that this an, since an is a convergence sequence, then it implies that an must be bounded. And if an is bounded, it implies that an mod can be written less than m for all n belongs to natural. Now just think about it. If I want to prove that Sn converges to 0, then I need to estimate. I need to estimate modulus of Sn, what it would be. So modulus of Sn would be a1 plus a2 dash dash dash. Let me write a n minus 1, and then I'm writing a capital N plus 1, and all these terms. This whole divided by n. And certainly this will be less than equal to modulus of a1 plus modulus of a2 dash 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 modulus of an minus 1 upon entire n, and plus I have already told you that if an converges to 0, then an minus 0 ka mod can be written less than epsilon by 2 for all n greater than capital N. So I think it can be written less than epsilon by 2, all these fellows like an modulus can be written less than epsilon by 2. This mod can be written less than epsilon by 2. So that is what I'm doing, writing them all less than equal to epsilon by 2. And I know how many number of terms these will be. These will be n minus capital N plus 1 terms divided by n. Don't forget this n also, okay? So what we have come up to, see, I know that Sn to the mod can be made less than, and all these fellows are less than m. So I'll write these are n minus 1 times capital M upon n. Understand that sequence is bounded, so all the terms a n mod can be written less than m. And all these things like epsilon by 2, and this is n minus capital N plus 1 upon n. Now, if n is sufficiently large, f is sufficiently large, then this can be written less than 1. So I can write this as n minus 1 upon m by n, and this can be written epsilon by 2. If n is sufficiently large, let's say n tends to infinity, then this bracket can be written less than 1. See clearly. And this bracket, you just see the first term here. If n tends to infinity, then I know that capital N minus 1 times n, this is a constant divided by n, this tends to 0. It implies that n minus 1 capital M upon small n minus 0 ka mod can also be made less than epsilon by 2 for all n greater than equal to, let us say, new number n naught. So again, this can be made less than epsilon by 2. This can be made less than epsilon by 2. So clearly, Sn mod can be made less than epsilon for some n greater than equal to some number. Let's say if it can be made less than epsilon by 2 by n naught, and if it can be made less than epsilon by 2 for, let's say, n equals to n1, then for all n greater than equals to maximum of n naught comma n1, Sn ka mod can be made less than epsilon, or in other words, I can write that Sn minus 0 mod can be made less than epsilon for all n greater than some number. Let's say, keep it for now capital N1. What does it imply? It implies that Sn converges to 0. And initially, please do remember, initially what it was written? It was written that limit xn equal to 0. Then it implies that limit Sn equal to 0. Please do remember, the converse is not true. Converse is not true. How to maintain that? Take example of xn is equal to minus 1 raised to power n. Take xn is equal to minus 1 raised to power n. Then Sn would be simply 0 if n is even. Just do it on your own. Like if n is even, then 1 plus 1, then minus 1, plus 1, minus. All these things will come in pair, and overall it will become 0. And if n is odd, then it will remain minus 1 upon n. All you have to do is add all these terms. Like x1 would be minus 1, x2 would be 1. X3 would be -1, X4 would be 1. So if you take n to be even, then all these pairs 1 minus 1, 1 minus 1, 1 minus 1 would come, and overall the sum would be 0. And if n is odd, then before just odd you have even, so overall 0, and then at odd place you will have a -1 and then divide by n. So overall this is clear, and I know that limit Sn would be then 0. If limit Sn 0, does it imply that xn converges to 0? No. Clearly, xn converges to -1 or +1. So in fact, it is divergent sequence. So if xn converges to 0, then limit xn can be written equal to 0. But if limit sn is going towards 0, you cannot say that xn converges to 0. Now just think about this. What do you think? What do you think about this series? Summation n equals to 1 to infinity a1, a2, a3 dash 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 an upon n. What do you think about this series? That is a1 plus a2 plus a3 dash 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 an upon n. Is that uh is that a what you can say? Is that a convergence series or is that a divergence series? And here ans are all positive. Just think about it. See, understand my point. I have already proven that for the sequence I've proven. Now, instead, if someone asks you about series, that is a1 plus a2 plus a3 dash 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 an, just remember this is greater than a1 upon n anyway, because ans are all positive. So indeed, this particular side would be greater than this particular side. And since a1 upon n summation is divergent, then it implies summation n equals to 1 to infinity a1 plus a2 dash 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 an upon n is divergent by comparison test. So this is an important concept that I wanted to teach you. So please do remember this concept. Let's just try to do one question. Just try to do one question. Just give me a minute. I'll write it. Okay. So what do you think about uh, this particular ANM giving it to you? I think you'll be able to do it. One plus 2 raised to power minus 2 plus 3 raised to power minus 2 plus 4 raised to power minus 2 dash 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 n raised to power minus 2 divided by n. Let us say this is your an. Okay, we want to know whether an is convergent or not, and we also want to know whether summation n is convergent or not. Okay, so how to go about this question? So see, I know that I'll write it here. I know that. So we know that summation 1 upon n square, where n varies from 1 to n infinity, is, or you can write k equals to 1 से लेकर infinity, is a convergent series. It implies what? It implies that Sn, which is equal to summation k equal to 1 to n, 1 upon k square, must be a convergent sequence. It must be a convergent sequence. So your an is nothing but it is equal to Sn divided by n. Let us estimate an modulus. Okay, one thing is clear, that if Sn is this, then Sn modulus would be less than some constant. And if you slightly remember, if you don't remember also, in first class itself, I told you its limit, you just take it for matter, is pi square by 6. Understand that Sn is an increasing sequence. And if Sn is an increasing sequence, it converges to its least upper bound. So in totality, I can write that Sn would be less than equal to pi square upon 6. So I can write this as, instead of m, I can write pi square upon 6. Even if you want to write m, I have no issues. So it implies that an modulus, which is nothing but is equals to Sn upon n whole modulus, certainly greater than 0, but less than pi square upon 6 and then 1 upon n here. Now, I know that as n tends to infinity, or as n is large, this entire thing would become less than 0. So I can write that pi square upon 6n minus 0, even if you take modulus or we don't take modulus, that is one and the same thing, because after all 1 upon n would be positive, and we made less than epsilon. It implies what? It implies that an minus 0 mod can be made less than epsilon for all n greater than equal to some natural. What does it imply? It implies that limit an would be simply 0. Okay, limit an must be 0. Now, what to say about summation n? What do you think summation n would be? See, it is 1 plus 2 minus 2 plus 3 minus 2 dash 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 n minus 2 upon n. Certainly, this is less than 1 upon n. Since this is divergent, it implies summation n equals to 1 to infinity 1 plus 2 minus 2 plus 3 minus 2 raised to power 3 minus 2 n raised to power minus 2 upon n is also a divergent series. It is also a divergent series. I hope it is clear. Now just think about it, about a few more questions that I'm giving you. Okay. So overall, please remember this concept. This is an important concept as such. So okay, let us consider that, just I'm giving you a question, try to do it. Let us consider that an is a divergent series, a divergent sequence, divergent positive sequence. And then we need to find what can be said about this series. Summation n equals to 1 to infinity 1 upon n raised to power. Now see, understand that an diverges towards infinity. Fine. What do you mean when I say divergent? See, whenever I'm saying that a sequence diverges to infinity, what does it mean? When I'm saying, let's say, xn equals to n, it is clear that as n tends to infinity, it will go on increasing to infinity. So then I should make this way. Okay, so I'm making a linear line. Initially, I was plotting x squared. Okay, so let's say this is how it is. Let's say xn is equal to n. Then I know that it can be made as large as possible. That is, xn would tend to infinity as n tends to infinity. Now, how to understand this? So one would say, okay, if xn is tending to infinity as n tends to infinity, I would understand this by saying that xn can be made as large as possible. Okay, what does that mean? It means that if xn is claimed to be greater than m, then I should find some number n greater than k. What do I mean? Again, I'm saying, if I'm saying that something is tending towards infinity, it implies that it can be made greater than any number. And for that particular number, you should have some n. That is, if I'm saying, let's say, xn is equal to n square, I know that this tends to infinity as n tends to infinity. Now, somebody would ask that, okay, I would assume that this is tending to infinity if you prove me that it is greater than 10 ki power 12. Instantly, I'll say that, okay, take n to be greater than 10 ki power 6. So for your given m, I'm able to produce some k. So for any given m, if I'm able to produce k as large as possible, if I take m as large as possible also, then also I'm able to reduce, and this is m in general, any positive value. Okay, it is any positive value. It's not that it is supposed to be large. I'm saying, can one not say that n square be made greater than 2? I'll say yes, indeed, it can be made greater than 2. Take n greater than equal to 1. Somebody was asked me, okay, tell me that n square can be made greater than 4. I'll say instantly yes, n can be made greater than equal to 4, provided you take n greater than equal to 2. And this applies to even large and large values. And it for every given m, so I'll write for given m greater than 0, an greater than m for all n greater than equal to some n. So if that is the case, only then I can write that limit an goes towards plus infinity. Yeah, diverges towards plus infinity. So an diverging towards infinity implies what? That for given m, an greater than m, I should be able to produce this n naught. So an is greater than m for all n greater than equal to n naught means what? It means that limit an is diverging, or limit an is simply tending towards plus infinity. Now here the question says is, what does question say? Question say that an is a divergent positive sequence. So an goes towards plus infinity, and I'm supposed to comment on the convergence or divergence of this series. How to do? So clearly, an is tending towards infinity. It implies an can be made, let's say, greater than 2 for all n greater than equal to some natural number n naught. What does it imply? It implies that an raised to power n can be made greater than 2 ki power n. And if this is the case, I know that 1 upon an raised to power n can be written less than 2 ki power n. Now from here, it is quite evident that summation 1 upon an raised to power n is less than summation 1 upon 2 ki power n. This is a convergence series. So by comparison test, this is also convergent. Okay, now what can you say about this series? The same thing is there, that an is diverging towards infinity. It is a positive term sequence. Then what can be said about summation 1 upon an raised to power ln n? What can you say about this? So see, it implies that an tending towards infinity, it implies an can also be made greater than 3 for all n greater than equal to some natural number, let us say n naught. It implies what? An raised to power ln 3 can be made greater than 3 raised to power ln n, and 3 raised to power ln n can be written as n raised to power ln 3. So 1 upon, so I'll write 1 upon, okay, instead of doing this, instead of using comparison test, I'll use something else. So instead of using comparison test, I'll use something else. See, just give me a minute. I'll use that so that it will be understandable. Okay, so an can be made greater than 3. It implies what? It implies that an can be written anything which is greater than 3, right? An can be written anything which is greater than, sorry, 3, so sorry. So sorry about it. N can be written anything greater than 3. So this is one thing that you should understand. See how it is coming. Please do understand, as n tends to infinity, as n tends to infinity, so an is greater than 3. It implies that 1 upon an raised to power ln n can be written as 1 upon 3 ln3 ln n. Okay, and I can write 1 upon n raised to power ln3 here, and you have this an raised to power ln n. Okay, I hope it is clear. I think okay, I can use comparison test. Okay, I'm so sorry about it. So see, if an is greater than 3, then an raised to power ln n can be written greater than 3 raised to power ln n, and I can do this. And please do remember, what is ln3? It is certainly greater than 0. Please do remember log x. This is the graph. And I know that for all x greater than e, log x would be greater than 1. So clearly, if x is equal to 3 also, then since 3 is greater than e, so I can write uh, ln3 would be greater than 1. And if ln3 is greater than 1, then this is convergent, then this should be convergent. So how should I write it? Okay. So if this is convergent, since this is convergent, this is also convergent by comparison test. Okay. Now, what do you think about this series? Now, again, the same condition that if an diverges towards infinity, then what can be said about this series? 1 upon an raised to power ln of ln n. What can be said about this series? Okay, so understand here no such generalization can be drawn. So I'm writing the series can be convergent as well as divergent. Let us see how. Okay, let us see how. Okay, for instance, just take an to be ln n. And I proved you initially in one of the questions that if I'm doing this question, ln raised to power ln of ln n, how to do this question. So see, what I do in this question, I will do this 1 upon e raised to power ln of ln n times ln of ln n. So ln raised to power ln of ln n is simply like uh, e raised to power ln of ln n times ln of ln n, which implies what? Which implies that I'm writing it here, which implies that summation 1 upon e raised to power 2 ln of ln, sorry, e raised to power ln of ln n whole square. Okay, so this is like ln of ln n whole square. Is that fine? Okay. And one thing that I need to tell you here is that if this is the series and I want to comment upon convergence and divergence, or let's say this is the series which ultimately goes on to become this, I have to comment upon this, then this becomes a new question. See, in order to solve this, just understand that ln of ln x whole square, if I just divide it by ln x, and if I try to take the limit x tends to infinity, so I'll get 2 times ln of ln x divided by again ln 1 upon ln x and again x, and this ln x would give me 1 upon x. So this cancels out. Again, I know this is tending to infinity. Again, I'll use L'Hopital rule. This is 1 upon ln x times 1 upon x, and again 1 upon x is here. So this cancels out. This becomes 0. It implies what? It implies that ln of ln x whole square divided by ln x minus 0 mod can be made less than epsilon or less than 1 for all x greater than some number, let's say x naught. Or in other words, if I'm telling about n naught, I can write that ln of ln n whole square upon ln n can be made less than. So basically it implies that ln of ln n whole square is less than ln n. So if I use the same e raised to power ln of ln n whole square, it will be less than e raised to power ln n. And that does imply that e raised to power ln of ln n whole square will be less than n, or 1 upon n will be less than 1 upon e raised to power ln of ln n whole square, or in other words, I can write 1 upon n will be less than 1 upon ln n raised to power ln of ln n. So if this is, since this is divergent, this will be divergent. So point number 1, with regards to this series, one can say that it may be convergent as well as divergent. So if I take an is equal to ln n, then this is a divergent series. Now, why I'm saying that it can be a convergent series? Let us see now. Why do I say that this can be also a convergent series? Let us see now. What I'll take now? Now I'll take an is equal to simply n. Now I know that this is something that I've done for you in previous class, that n raised to power ln of ln n is simply 1 upon e raised to power ln n, and then again ln of ln n. Okay, so e raised to power ln of ln n, or you can do this, or otherwise see. Otherwise, I'll do this one thing. Instead of going this long way, I'll do one thing. See, understand my point, what I'm trying to explain now. This is the last question in this series now. Then we'll take another set of questions tomorrow also. Please do follow all these questions, and please tell me in the feedback how much you are liking these questions. So I know that ln of ln n can be made greater than 1. Just see how. Ln of ln n can be made greater than, so it implies that if I take n greater than e ki power e, so certainly the next natural number to this would be e raised to power e greatest integer plus 1. If you take even approximate e as 3, then 3 raised to power 3 is simply 20. 3 raised to power 3 is 27. So something around 28. So beyond 28, I can say that for all n equals to n naught towards infinity, this can be written as n raised to power something alpha, where alpha is greater than 1. Understand my point. Please do understand my point. Let me write ln of ln n as alpha. Okay. Now I know that for all n greater than e ki power e, and if I want to find the natural number, it would be e ki power e greatest integer plus 1. It will give me that natural number, and beyond it, I understand that this is greater than 1. So basically, this series can be written in this form, and 1 upon n raised to power alpha. If alpha is greater than 1 for all n greater than equal to n naught, I understand that this series would be convergent series. So nothing can be said about this series. It can be convergent as well as divergent, provided an tending to infinity. So summation 1 upon an raised to power ln of ln n may converge also and may diverge also. So I hope in this short lecture, I've been able to explain you how to apply comparison test. In the next lectures also, I'm going to again do a few questions regarding comparison test, and then we'll move on to a new set of questions. Till then, take care. Bye-bye.